Okay, so why don't we get started since it's 5 minutes past half past. So we'll so if nobody has any sort of urgent questions right now, feel free to ask at any point later, of course. But we'll just get stuck in back where we left off yesterday, which was actually, if you remember, the very end of this lesson on indexing, slicing, and subsetting data frames. So it was about selecting the data we want, both in terms of range-based and label-based, so numerical range-based, based on labels, indexing with labels, and also by applying conditional selection criteria based on the properties of the data itself. So whether a given field has a certain value, is greater than or smaller than a certain value, is not equal to a certain value, etc., etc. And clearly that's relevant to be able to know how to select exactly the data you want. The point where we got to yesterday at the end was this final challenge. I think we actually started looking at the solution, so we'll just continue there. So the idea was, given our data frame that we still were using all throughout yesterday, the surveys data frame from the species comma separated value file. The question was create a new data frame that only contains those observations with sex values that are neither female nor male in the data. So marked neither as M or F, and find out how many rows there are and check that the number of entries basically in that new data frame is equal to those number of rows in the original data frame where the sex field is regarded as null, or maybe I should say, as you'll see, is equivalent to not a number, basically where it's not recognized as a number. So we started looking at that because I remember talking about the mask, how that works there. So, okay, so the way to do that, one way to do that would be using this conditional. I'll expand the window a bit so it's clear. So creating a conditional here, which is saying that if for all those data entries in the data frame surveys df, where the field value sex is in either belonging to M or F, so you've passed in a list of potential values here, and then we put the negation here. So if it's neither M nor F, to create a new data frame, so this selection criterion here. So basically, what this amounts to is effectively, as we saw yesterday, is a mask. So we can have a look at that just to remind ourselves. In data, so if I load my surveys, df starting from scratch again is of course. You might as well do this yourself and follow along because we'll use the surveys data file again, I think. Import pandas as PD. You may have your session still open from yesterday, but if not, you can follow along and do this as well. So then surveys data frame is equal to pd.read CSV. The file name was surveys.csv. That's it. And then we'll take this conditional that I just explained and see what that is. So what that shows is that evaluates to a Boolean mask, essentially. So where it's true that the condition is satisfied and false where the condition is not satisfied. And if we use that as an input argument to if we use that just to basically get those entries of service df where that is the case, then you can see that that's going to apply that input mask to all the rows, and selecting only certain rows. So you can see here, for example, the first index that appeared is 13, so indices rows 1 through, or I should say 0, with index 0 up until and including index 12, have been eliminated because there, as we can see here, for the first 5 values, that condition was not satisfied. So those have been eliminated. Okay, and then here they take a copy. Why? Because to make sure that we don't modify the when we do anything with this new data frame, suppose we were to change any of the values, to make sure we don't modify the original data. So having done that, so I simply say left-hand side is equal to that result. Oh, dot copy was forgot. Then print length of, well, if I just do it like this, output. So that many rows, so that many entries satisfy that they are neither belonging to M or F in the original data, and that's out of, if you remember, that's out of a total of something like 33,000 rows in the original data. And then the question was, verify that that is the same number as number of rows in the original data frame where the sex is null. And we say is null, we have this condition that we can, well, not conditions, or with this method which we can do to test the value. So we're basically asking the question of where is it true where the sex field is null. That will again return a Boolean mask. It's no surprise that it should look similar to this one. That's essentially what we'll end up verifying just for consistency. And now what this does here, which I explained yesterday, which wasn't maybe immediately obvious, doesn't explain in the course materials, is it determines, it works out how many rows those are by doing the sum, and that relies on the implicit knowledge that in Python false is equal to 0 and true is equal to 1. So when you do the sum over those entries, everywhere it's false contributes 0, everywhere it's true contributes 1. So that effectively ends up amounting to the same thing. And okay, the consistency is there, so that is the same number of entries as the ones that satisfy the logical condition where the sex field is neither M nor F. In other words, that tells us that there's no other data apart from data that is where it's M, data where it's F, and data where it's null. Now, what does that null mean? PD.is null. I think we looked at that briefly yesterday. That function takes a scalar or array-like object and indicates where the values are missing. So typically not a number, or also there could be none. Yeah, so any entries like that, which would appear in our data frame, because the read CSV function would have by default assumed that missing values where the fields in the file have no entry, it would label those as nans. Okay, so that's consistent. Then secondly, create a new data frame that contains only observations that are sex male or female and where the weight values are greater than 0. So we can do that here. We're doing the same selection here. It's in M or F. So basically now we're not doing a negation. So now we're not taking the null values. We're taking where it's genuine data, and we're combining it with conditional where the weight must be greater than 0. And for those in that resulting data frame, we take the so let's see, we'll show what that gives us. We extract specifically the sex weight and the columns sex weight and plot ID. So just to make it clear, if I remove those final, let's see. Yeah, just to clarify, by the way, this ampersand here allows a. Oh no, that's a conditional combination of these two conditions. So so yeah, we've extracted our specifically sex weight and the plot ID because that's what we care about. And then if we want to plot this, we do it with what we care about is the average, i.e. mean weight. So that's why we compute the mean, and want to group these things by sex and by plot ID. And if we do that, Yes, I've not defined stack selection. That is correct. And I must include these bits. Okay, and then if I say group that by, then you see that we get basically what we want. So I need to make sure that I save that, and we're actually overwriting the original variable, or rather we're pointing the variable now at this new data we've created. And then plotting that should, that's because I've not imported matlib.pyplot as plot. Okay, yeah, so then we get what we want. Okay, so yeah, you may have gotten that already yesterday or had a look at it between then and now. But this is just finishing off this final bit of this episode. So what we've seen here then is we've covered a variety of ways of selecting the data we care about, and we tried to put it all together. We said we can use indices, slices and range, column headings, i.e. label based. Things to remember is that the numerical addressing for lots of Python iterable objects, integer addressable objects, integer indexable objects start at 0. Yeah, so if there's any questions about that, we can go ahead with the next session. So let's have a quick look actually to remind ourselves what we've got. So I think overall, let's have a little overview since we're in the second day after finishing this lesson. So we've covered so far introduction, starting with data, indexing, slicing, and subsetting data frames. So now we'll cover more or less the remainder. We'll see how far we get. I propose to not cover this final bit of SQL databases. We probably won't have time for it anyway, but I do aim to get ahead, make progress that we can cover a reasonable amount of material in the visualization part. So I think with yesterday, we spent a lot of time on the basics. I think it was useful because, well, based on what the course is aimed at teaching, it's good to build this kind of solid foundation. And if you have this basic familiarity, you can hopefully go away and figure out a lot of details yourself. So what you may find is that, although satisfying, so these two parts will be satisfying because you'll be able to make nice plots and learn some specific ways in which plot9 and matplotlib can be used to do that, in particular dealing with data frames. There's nothing kind of conceptually as kind of new, perhaps, as earlier on, where if you're not familiar with it yet, it's kind of just getting used to how Python sort of fundamentally, and Pandas in particular, works with data and some of the syntax there. And that approach will, as I already said yesterday, how to address things with indices or labels, and that kind of, and how you form lists and things like that, how you select data, that will sort of translate across. Okay, so and we'll see in some of these lessons, certainly in the next lesson, that some of the things that are here covered there were already covered yesterday. So and already also in the data workflows and automation, there's some things that are kind of repeated from yesterday, even if not in the materials. I sometimes already mentioned some things. So I think we'll make some good progress and get towards the visualization part, so you can actually get some nice plots. Speaking of which, if anybody had any problems still with using plotting within the terminal window, either within Python or IPython, I do suggest that Jupyter Notebook is probably the most sort of the most likely way to work without issues. Yeah, because you won't have to deal with this plot.show thing. Just keeping in mind that within Jupyter Notebook, I didn't find it necessary, but there is an advice somewhere to as we'll see, there's an advice somewhere to inline your to tell. Let's see, we'll come across it anyway, but I thought I would just find it. Yeah, here. So there's, when you're using Jupyter Notebooks, the recommendation is that you use this command, matplotlib inline, which does require you to, well, does it require you to load the matplotlib module by doing import matplotlib? I don't even think so necessarily, because one thing I didn't mention was that this percentage sign, I didn't use it myself in IPython, but if you remember, I said that IPython has these sort of magical commands where I just realized I was gesturing, trying to get my webcam working because I was gesturing, making quotation marks in the air, which is no use if you haven't got your webcam on. So IPython has these magical commands that are not actually Python code, but are just stuff that works in IPython because it's convenient, and that allow you to use familiar shell commands to interact with the operating system, interact with the file system, and do things like time your code by using the time it command, stuff like that. So in principle, all those magic commands, you're supposed to, formally speaking, they start with a percentage sign, and then the command to indicate the percentage sign indicates that they're not Python code. But IPython recognizes it anyway, even if you don't use the percentage sign. So if you just were to type matplotlib inline without using the percentage sign, I think that A, it will just recognize it, and B, because it's a Python, because it's an IPython magic command and not actual Python code, it's not like you need to import matplotlib package. I could be mistaken about that final point, but you'll notice soon enough. So basically the only reason the only thing in Jupyter Notebook you may want to do is this inline thing. Although, well, this may be a version. This document, this course materials might have required that for a particular version of Jupyter Notebook and a particular version of matplotlib, because when I used the install, which is sort of the latest Anaconda install with Jupyter Notebooks, generating plots with that, as in this session, for example, I didn't need to do this. It just worked. So, but that's just letting you know, just in case. Okay, so let's continue with the next lesson, which is on data types and formats. So the point of this lesson is to look a little bit more about the data that's stored in the data frame. It's a little bit funny that they have organized it this way around, because you might think, well, you might start off with that a few lessons ago when we first started reading data into data frames from file. But I mean, doesn't really matter. It's chicken or egg. You start to use stuff, and then when you realize something's not working the way you expect it to, then maybe you need to pay more attention to what's actually happening under the hood, and to understand a bit more about how the data frame is structured. But some of this we already looked at yesterday in the context of understanding the data frame structure. So so we'll have a look at this. We talked about the types of data already yesterday. So if you have a data frame, then just close my image. So if you have a data frame like the surveys data frame, if you get the D type, D types, there we go. So it has a D types attribute, which shows you simply a list of the fields or columns data that are present, and what underlying data type, Pandas data type, Pandas has decided to use to store the data in each of these columns. So it's worth noting that each of these columns, essentially each one of these series within the data frame, has a defined data type that's different from lists, from Python lists, as I said yesterday, because Python lists, all the elements can be different types. Pandas imposes that the Pandas series within it, each Pandas series is of a defined data type. And you can see why, because just like I said yesterday, the core array that we usually use in the most basic array that we use to store data in Python, numerical data, is a NumPy array. And that also has defined data type like int or float. And the reason for that is because it's faster, essentially. Enforcing that means that, like I said yesterday, the Python interpreter, when it's processing data, numerical data, in some kind of array NumPy array or Pandas series that has a defined data type, it's faster because it can make certain assumptions about what data it's going to encounter, the size of that data, and it doesn't need to constantly check what kind of data it's encountering. So we've seen these data types before, integer and float. We haven't come across datetime or time delta before. So yeah, this is just showing already what we looked at yesterday, the kind of just checking what have we actually been dealing with. Our service data frame, what type is that? Yes, it is a Pandas core frame.data frame. If you're trying to access help, by the way, you can actually, if you're trying to look at attributes of the data frame, you can actually do a shortcut where instead of typing, for example, help pandas.core.frame.data frame, like that, Q to exit, you can actually do, I think, pt.data frame as a shortcut. So that's useful because if you've got a function that, well, it's just helpful as a shortcut. Okay, so we already looked at, okay, you can get the data type for one of the fields like this. So each of the series, so we saw yesterday that if you address with a label, for example, one of the columns to extract one of the fields, that extracts the Pandas series corresponding to that label, and that Pandas series also has this additional information. And to directly access the type attribute, you can do this as they're proposing. O for object, fine. Okay, so this is just reminding you / introducing some useful shortcuts to be aware of. Now, some of this we already looked at yesterday as well, working with integers and floats. So we saw we could, if Python assumes that if you're adding two things which it thinks it's an integer, it will say the result is an integer. Similar subtracting. With dividing it, it actually changed between Python 3 and Python 2, where if you're using older Python interpreter, Python 2, then it would actually truncate the fractional value of the result, and would actually go to the nearest integer. I think it would actually go down to the closest integer. But in Python 3, this quite sensibly results in a float. So yesterday there was a question about, I think Nahal, you were asking about conversion of numerical data types. So we can do conversions, explicit conversions of numerical data types. So this is an example where if we define a to be a number that Python will interpret as a floating point number and will store as a float, then we do an explicit, what's called a type casting. So we explicitly cast or recast, ask Python, ask the language to give us an integer version to convert the float, to convert a to an integer. Then what you see what it does is even though it's closer to 8 than to 7, it doesn't round up to 8. It just cuts off the fractional remainder. So that's something just to be aware of if you're ever doing that, whether that's what you want. There'll be another function to do the rounding up or rounding down. You just have to choose basically. The other way around is unambiguous, of course, because you're not losing any information if you go from integer to a float. So if you define b to be a number that Python says an integer, you get the floating value of that. Then you just change the representation, and there's no ambiguity, there's no loss of data, as you would expect. Okay, so some useful stuff here. Okay. See your question, Alba. How's the command to save the plot on the PC instead of plot.show? Yeah, it is plot.savefig, and then savefig, I think you just give the name and then .png, for example. I think it might also be in the Etherpad. Let's have a look. So, yeah, line 97 here. Okay. Yeah. So here's some additional stuff that's useful to know about. So you can we talked about converting individual numbers. Now the question is, when we go back to our data frames, can we convert entire series in our data frame to a different number? And yes, we can. So we can convert all the values in, for example, the field in the column in the series corresponding to the record ID. We can convert that from, well, what was it? It was, well, you can imagine that it was an integer, but let's confirm that. Surveys underscore df record ID dot d type. That's an integer. Yeah, we can ask it. We can ask Pandas to convert that to a float by using the dot as type method, acting on a series. So that's see what it tells us. Yeah, so we can see that that returns a new Pandas series where all the values are now floats, and consistently the d type is now identified as a float. So that's a way to do numerical conversion. So why don't you have a go at trying this? Shouldn't take long to, assuming you have the surveys data loaded already. And yeah, go ahead and put in the chat what you think is going wrong. Or of course, feel free to raise your hand and unmute yourself if you want to just say it rather than chatting. It's fine. So the first thing should work. This one should work. It's similar in nature to the one we just did. Although maybe you spotted the difference already. Here we're saying convert something that is an integer to a float, and then before the previous line here we were asking convert it to a float 64. You're asking what's the difference? Well, actually, there's not a difference. You can Pandas will understand both. In both cases, it will use float 64 as the real how it defines the d type. So it allows you to simply say float rather than float 64. It understands both. So this one should work. Anybody tried converting the weight field, so with weight here, as type int? And do you have any idea why that doesn't work? So it shouldn't work. If it works for you, then that's also interesting. I'll just try that. Let's put a little poll. Yeah, that's right, Thomas. So if you remember from yesterday, still the weight field, there were quite a lot of apparently empty entries in the CSV file. So when Pandas ingested that with read CSV, it categorized those elements as NANs. And so what you're trying to do essentially when you're asking it to convert the Pandas series with the weights, that entire column, into integers, when the first time it comes across a NAN, it's saying, well, I mean, what do you? I mean, you just can't do that because it's not a number. You're asking it to convert something that's not a number to an integer. So it's going to complain. No surprise. So it says casting NaN error. We cannot convert non-finite values like a NaN or something that's infinite to an integer. So we're going to have to somehow deal with NaNs, and that's we already did something with the NaNs just at the end of the last lesson. We did some selection criteria to find them. Now we can look at various ways of dealing with them, because that's obviously something that comes up a lot if you're analyzing pre-processing, post-processing data, also to try and visualize it. Nicely enough, some of the it might not have been obvious, but the basic plots that if you ask, so with these data frames that we've been creating and plotting them, it's what Pandas does is quite nice in how it deals with NaNs, in that it actually just, when it plots stuff, it mostly ignores the NaNs. So by default, you kind of get plots out with even without having to do the cleaning, so which is nice because it means you can immediately at a glance see what your data is without having to do a lot of cleaning. But obviously, if you're going to do anything more, you need to be aware of where your NaNs are. You need to do something with them. Okay, so so this is just saying that we have to somehow deal with them. So another nice way in which Pandas deals with NaNs without bothering you, without forcing you to deal with them immediately, is that when we asked Pandas to give us summary statistics by using the .describe or .mean or whatever to get statistics on particular series within the data frame, like for example the weight, it was giving us values all the time, no problem, even though there were NaNs. So you might think, okay, what's going on there? So basically it's just skipping them, right? So it's just excluding them, which is nice, I guess. I mean, you get stats out, but it is good to be aware of that. So the question is, of course, what do you do with NaNs? Well, that depends on your application. Depends on what you want to do. What you can do is you could. Well, one choice would be to replace it with something else, with an actual number, like 0. In some cases, if you've got like, I don't know, I remember seeing one case where it was like LiDAR data from so surface, geosciences thing was like a satellite, or no, LiDAR data. It's not satellite data. LiDAR data is basically this plane, I think, that flies overhead with a LiDAR. So there the convention was that missing values were indeed something like -9999, and depending on your, I don't know, piece of lab equipment, microscope, telescope, whatever you've got, it might render NaNs. It might render missing values in different ways. So it's good to be able to deal with that. Of course, if it's a numerical value if it's any numerical value that is already, so you need at the time when you ingest your data, you need to be aware of this, because if you read CSV, the Pandas read CSV, which we use to load our data, but it was happy to by default categorize missing values as NaNs. But as we can see, pd.read CSV, I think I talked about it yesterday already. So there's this in the signature of the file, of the function, there is this argument called NA values, which basically is tells you something about. So it allows you to define, to tell Pandas additional strings to recognize, and i.e. to categorize automatically when ingesting the file as being missing or as being somehow needing to be loaded into the data frame, labeled as nans. So you can use that to specifically, for example, say that if when you read your CSV, say NA values equals minus 99999, that means that it will automatically, when reading your data, assign nan in the data frame for wherever the CSV file has minus 99999. So that's exactly what you want in order to deal with missing data, or data that you somehow don't want to include in statistical calculations, etc. Because obviously that could, having those kind of values and not dealing with them, could just completely give you wrong answers, or strange outliers in your distributions, etc., even if they don't affect the averages by much. So so it's good to be aware of that. So there's an exercise, so we can see, for example, how one of the ways of dealing with that is to do something similar we did at the last. So this here looks very similar to what we did in the last lesson, but it's using the method is NA as opposed to is null. So Catherine, your question was, how do you do that? Do you mean how do you tell? Sorry.
Yeah, I meant just because in my field no data is minus 9999, and so it is handing. So I just was looking exactly on those instructions. Does it say how to do that? Or
yeah, so it might be a little bit cryptic, so it might be good to find an example, but it's essentially saying that what you can do is pass as NA values, you can pass a scalar, i.e. a number. You can pass a string. You can pass a something that is a more than one scalar or string, i.e. something that's a list, or something that's a dict. So the way, what I would say is that, so let's imagine, well, let's test it. So if we've got, so let me just go into our, I'll make a copy of a surveys file so I don't mess up anything important. So missing data. Well, I'll call it 9999.csv. I'll just go in there and I'll mark something as very first entry as so I think yeah, so I think so minus 9999. Right, so that value there, and then what I'll do is I'll say p.read CSV, and first of all I'll do it the way we've been doing it so far, which 999. I'll just read it in like that. So there you can see it's right there. So we can spot it now because we're looking at it and it's an obvious value that isn't hidden. But obviously it could be hidden. So what do? We say, well, you know what? If there are any values there, and I'm guessing here, let's hope this works. And if they are equal to minus 999, then mark that as NA. Yay! So that's done it. Yeah, so that's the way to do it, and you can have more than one value that you want to mark as a nan. And I think if you the option to pass a dict probably is more flexible still, so that rather than just making it a nan, I guess you can maybe say, okay, if you ever find something that's this, then mark it as that, and categorize it as this. So if you mark it and multiply, et cetera, et cetera. So it's really flexible. So you can basically use it. You should be able to use it for whatever your data needs.
So just so you tend to do that when you're reading CSV files. So that's not necessarily important. So I guess maybe that's the way. Yeah. Could you filter it after you've read it? Do you see what, or is it? Because I guess that's doing that, setting that when you're reading it in, rather than when you're like interrogating the data or what have you. I guess there's two ways, isn't there? But this way is maybe the neatest way, is it? I guess.
Yeah, there's certainly more. There's certainly at least two ways. There's probably even more. It's kind of up to you. I mean, I guess to me it seems like a nice thing to do it first of all, because unless you know that you might want to use the actual value of -999, then why not do it? But that's up to you. I think you just have to judge for yourself what's convenient.
So thank you very much. Sorry to interrupt.
No, that's fine. It's great. Yeah, I think the echo was from from Catherine. So yeah, apologies. Evgeny, do you want to say anything about what your suggestion to filter first to get a subset?
So I guess that's already been mentioned. But what I had in mind is to clean the data in a way that it doesn't have any missing value first. And this tidy format also means it has a format where each sample is on a separate row and each cell contains only one value and exactly one value. And each feature of the dataset is a column in a nutshell.
Yeah, and what would you prefer to use to do that?
I think the Pandas verbs can be used to do that.
Okay.
So kind of use masks to first exclude the records that are not complete. Yeah, it depends. That's why there's probably always some corner case to consider as well.
Yeah, there's definitely more than one way to do it anyway. Okay. Yeah. So what I think we got to just before then was to talk about this is NA here. So just before we had in the previous lesson we were using the .is null, if you remember, to tell us whether values were nans. So now there's is NA. What's the difference? Well, as it happens, right. So these are just aliases for the same function. So don't get confused by that. They both are the same thing. So if we look at the help for the pd.isNA, we can maybe remember that the description is the exact same as the description for the pd.isNull that we looked at just earlier. So it is the same function. There's one, so there's a function here, fill NA, which you can use to replace all nan values in the relevant series or data frame, depending on what precedes the .fill NA with zeros. So replace all the nans with zeros. Is that the right thing to do? Depends on your case, right? Obviously, it's going to affect the statistics. If you've got lots of zeros, the zeros will not be excluded from the statistical calculation. So they're going to affect the mean. So the example it's giving here is that original calculation showed us that the mean was, I think it was like 42 or something a year ago. That was the original mean from the survey's data. And if we use the fill NA function to replace all our nans with zeros for some reason, then obviously it's going to affect the mean. Then the mean is different. So that might not be the right thing to do. It all depends on your data and your code. So you just have to be aware and decide how to deal with it. Yeah, so there's just okay. So here one way to deal with it could be so to use the fill NA function with an input argument. So by default, fill NA fills all nan values with 0, but you can give it an optional input argument. Apparently, you can have a look at the help file, the help documentation for fill NA. So if you don't want it, if you don't want the filled values, the substituted values for nans to affect the calculation of the mean, you could simply make them equal to the mean, right? So they won't affect the calculation of the mean because they can affect other calculations. So yeah. So the point that they're making as well is just to be aware and to decide, basically. Okay, do you want to try this challenge here, which is counting the number of missing values for each of the columns in the survey's data frame? So what we want is, for all of the columns, what is the number of nans, essentially? Just give everyone a minute, a couple minutes or two to just try that. There's no rush, but yeah, put the poll up. So if you did already work through that and find a way to count the number of missing values for each column, then yeah, just indicate it in the poll. And if you like, you can share your solution in the Etherpad as well. Okay, it's all right if you haven't completed. It's more important that you at least get a chance to think about it, rather than just listening to me talk, because it's just a way to engage with stuff. So even though I think only a few people have said that they've completed that challenge, I think I'll talk about that in the interest of time, because I'm eager that we get through some of this a little bit more and we get into the plotting stuff as well. But at any point, obviously, it's more important that you get out of this what you want. So if you have any questions, we're not rushing for the sake of rushing, for the sake of getting to the visualization necessarily, but at any point, just ask questions or ask to go over something again. That's absolutely fine. So what they suggest, well, let's see if anybody's put anything in the Etherpad. No. So what they suggest as an option is using, this is something that we didn't necessarily know. We used the count function or the count method already yesterday in a few cases. What we didn't realize, and probably just took for granted, was that count skips also, like some other pandas functions, skips nans, so it doesn't count nans quite reasonably. So it indeed tells us the number of the genuine observations for each series. If we ask count, if we call count on a series, or if we do data frame dot count, it'll give us all the non-nan values and all the columns. So what it's suggesting here is that, well, that's a good question actually. So what I just said, is that true? Okay. Yes. So that actually, it doesn't tell you the number of missing values per column. It tells you number of non-missing values per column. So in fact, I think that's what I base my solution on, which is a little bit different from that. I just said, yeah. So essentially, what I've just done tells us the number of genuine values in each column. So logically, the number of missing values in each column is the number of number of values in that column minus the number of genuine values. And in order to be able to, so if I want to get the number of values in each column, I know it's the same. It's all just the size of the data, number of rows in the data file, which is something like 35,000 or something. But so it's stored in obviously service df.shape or length of service.df. So that 35,549 is the number of rows. But if I want to subtract in one fell swoop, these numbers from 35, I'm just going to create, what I want really is some kind of array, essentially, array-like object that has the same size as this, the same as the number of columns, and for each entry being equal to that 35549. Or actually, as we saw yesterday, we can do arithmetic operations with scalars and arrays. So what I can actually do, I can take that length of the surveys, and I can actually subtract. So the first guess would be to subtract the above. That so that works. Yes, that works actually. Okay, so the solution even slightly simpler than I did, which was to say I've got the wrong axis, so I want my axis to be okay, that is the default, so that's fine. So what I've done is simply used count to tell me how many genuine values there are for each column. It's shown here as rows, but as you can recognize the labels, these correspond to the labels of the different columns in the data frame. And subtract and find the difference between the number of total rows in the data frame and these numbers. And for all of these columns, they were the same, so there were no missing values in those columns. And for these columns, those are the respective numbers of missing values. And we recognize from last lesson already that the 2511 is indeed the number of missing values for the sects. So that works. The solution they took was to iterate explicitly over the columns of the data frame for each of them, get a query, use a .isNA to query what is not a number, and then get the length, get how many rows that's true for. Now, I wonder if there's even an easier formulation, which might be to say surveys df the entire thing .isNA. Does that work? Yeah, okay, so that works, but then you still have to, yeah, it tells you, gives you all the mask, so you still have to do some, yeah, work to either do sums or find the length of those rows, length of those columns. But yeah, either approach will work. And as it mentioned here, you can use isNA or isNull, as we saw. Those two are identical. So yeah. That's one way to figure out number of values, number of missing values. Okay, yeah. So Thomas, you had surveys. Do you have is null? Not some. Yeah. So when using the sum. Good question. Summing of columns is the use of mass fastest total in other ways. It depends. So I'm not going to make any general statements. That's dangerous. I'm going to say use time it. So if I use time it on, so let's see, your approach. I didn't test whether it gives the right answer. I'm assuming it does give the right answer. Do that. Yeah, okay. So that takes sort of that amount of time estimated. Let's see, let's get my answer, which was this. Let's time that. It's faster, okay. So let's take their solution. Oh, I think it's a little bit annoying because it's because it's an iterating loop. So I think I'm going to just, if I want to do that, I have to just define a temporary function which does that. Let's see if this works. So yeah, we'll get to defining. We defined a function yesterday, so you've seen the function defined before. But I think one of the lessons after this about automation and workflow actually goes into more detail about how we define functions. But I'm just doing it now in order to be able to use the time it command. The time temp. Oh, okay, I know why that's happening. It's because I've defined a function which explicitly prints that out. I'm not going to print that out. I'm just going to assume that. So asking it to do a little bit less work, but it's going to give reasonable results. So yeah, that's like that. So my answer and this answer are both very similar, like 11 and 13 milliseconds. I think yours was 40 or something. So does that matter? Probably not. It depends on how much data you've got. So, but the answer is is probably don't assume, but try it and try timing different formulations. So I'm not comfortable making general statements about using the masking and summing being faster or slower. So it's often the case that it's usually the case, and this applies not just to Pandas but to NumPy and Python in general, but especially things involving big arrays of data of numbers like NumPy arrays. It's usually, if there exists a predefined function in a package to do something, then it's usually faster than trying to code it yourself. I mean, maybe that's an obvious statement, but so it's worth finding if there are functions to do what you want to do. When I say functions, that can be a bit, it might appear to be untrue by virtue of the fact that when you're adding two NumPy arrays, the fastest way to do that can be simply to definitely not do an explicit for loop where you say for all the elements of the array, add create in the value of the element in the array that is meant to contain the sum is the sum of the two elements in the two arrays that you're summing. So don't do explicit for loops, but do plus. You simply do one array plus the other array, and it seems like, well, you're not using a function to do this. You're just using plus, but actually the plus there is overloaded to do something clever, but it's not important. Forget. I mean, details beyond the scope of this course, but yeah, time it basically. Okay. Good. Yeah, let's continue. So almost nearing the end of this bit. So it's finally just the idea. I think the idea of this lesson is very much that you're basically using conversion and dealing with missing values and nans, so that you kind of maybe incorporate using Pandas in your workflow as a way of cleaning your data, and meaning reading it in, doing some stuff to deal with missing values, and then writing it out again. I don't kind of remember so far if yesterday we wrote out any data to CSV file, but just like we read it, we can also read it. Sorry, just as we read it, we can also write it. But first, let's try a different function that's actually very convenient, which is called, for cleaning data, which is called drop NA, drop nans. So what does that command do? That command actually just removes all rows in your data frame, or probably also works if you call it just on a series, on one individual series. Removes all the rows where there is a nan in any of the columns in the data frame. So that's a thorough clean in a way. You're just saying, okay, some column has no data, so I'm just going to remove that completely from my data frame. So that will do that. If you were to do that, then you'll see that there's about 5,000 rows that were removed. And you could say that's it. If that's what you want to do, remove anything that's missing value anywhere. Remove the entire row. Then you can do that and then write it out to a new CSV file using the name of your data frame, that .toCSV. What you would use if you want to write out the cleaned one, you would do this one, DFA underscore NA .toCSV, give a path to what you want the file to be called. Oh yeah, there's, so an optional argument index equals false, because if you remember, when Pandas reads in the CSV file, the data frame that it creates, like our surveys DF, it's got this first unlabeled first column, or zeroth column, you could think it would call it. In fact, it is zero, so right, zeroth, because oh no, of course it's not. Yeah, no, it's not. It's not indexed like that. DF dot. Yeah. Okay, that's the first row. Same because of integer. Yeah. So my point was only that the surveys data frame, any data frame, has this first unlabeled column, say, which is the index, and that you probably don't want to include in your CSV file when you write it out, because that wasn't in the original CSV file that you read in. It's just something that Pandas added. So therefore, to make sure that that index doesn't get written out to file, you include the option index is false in your toCSV command. And yeah, you can use that. And actually, yeah, it'd be good actually. So this gets used later on, this data file later in the workshop. So in fact, why don't you go ahead and actually do this? So create this DFA NA by doing surveys df.dropNA, and then outputting that to a data file, which you can then use later on in a later session. Let's see, where am I? I'm in the data directory already. So my path will just be the name of the file, which, okay. Right, so if I do ls again, magic ls command, see if I use percentage sign, it works as well. But, that file is there, and that contains now no nans. So if I look at surveys, if I look at what we call df_na, you'll see that even, at least in this very quick overview, you don't see any nans. The rows where the weights was nan are gone, it's all gone. There's no missing values. Okay, so this lesson was about looking at data types, conversions of data types, looking at nans, dealing with nans. That's it really, and writing out your CSV file. So it's just part of essential stuff to be able to do in a workflow. So we'll make a start. We've got a break planned 11. We'll make a start on the next session, which is quite a useful session. So just trying to see if there's anything that I missed out mentioning that I wanted to mention. Oh yeah, one thing worth mentioning was that you may at some point, I know I probably at some point certainly tried doing this, not recently, but when dealing with nans, you might have thought, okay, well, can't I just make some conditions where I say, if I want to, for example, check whether the weight field in my data frame is a nan, and then use that as a mask, just as we were using other things like if the value of a weight is greater than 0 or something. Can't I just check if it's true? In the same way that I say, before I was saying, is it greater than, I don't know, 5.0? And I got some result from that. Some weights are bigger, some weights are smaller than 5.0. Can't I just check if it's equal to a nan? No, nan as such is not defined. I mean, when you look at this, it might, it's written as NaN, but that's just a representation of what's there. It's not, you can't sort of check logical equivalence like that. So that's why there are these functions like is NA or is null. So yeah, that's just something to mention. Okay, so let us spend a little bit of time before the break looking at the next session, which is which one is it, number 6? Looking at combining data frames. Okay. So what's the idea here? So the idea is that we have, suppose we have more than one input file, basically, that we somehow want to, so we have information that's linked somehow in 2 different data files, and we might like to create either a combined, it could be the same, it could be data with the same structure. So it could be that you have basically, 2 files with completely identical layout in terms of the number of columns and the column labels, and the type of data that's in there. And it's just, I don't know, more data. So more time series from your device or whatever. And you might like to combine the data from those 2 files into a single data frame for example, I don't know, say to plot a time series over an extended period of time that's covered by multiple files, multiple input files. So that's one option, and that's the first case where we're talking about combining data from multiple files into a single data frame using concatenation. So concatenation basically being where you basically just take the data and add it before or after the original or the first data in various ways. Then we'll also look at another case where the data is in these two files is not structured identically, but is somehow related in a way that allows us to create some additional insight. So we'll see an example there where the original survey data in the file we've been dealing with so far already included something called the species ID, just a 2-letter code. And there's another file that contains in the input data, which will fetch at when needed if you haven't already fetched it, which is called species.csv, and that species.csv contains let's see, that species.csv contains it's a comma separated value file as well, but it's quite short. It's only about 50 lines long, but it contains for each of those species 2-letter codes. It actually contains more information. It contains the genus and the species and the taxa. So and essentially what this is a canonical list of the species, what these IDs, what these 2-letter IDs actually correspond to. So it's like a lookup table for the for additional information about these species. And you can imagine that you might like to use that information to, I don't know, for one thing, plot some of the data in the survey results. But it's nice to have this 2-letter species code because it's very brief, and that's all you need to be able to identify the species in the original survey data. But if you don't necessarily store all the additional information, all this again and again and again every time that a Amphispisa bilineata bird appears in the survey. So you just store it as 2-letter code, nice and efficient. But at some point you will want to pull in this additional information about that, and that's where merging data frames comes into play, where we draw in data that is linked via so-called key, but that is shared between 2 data frames, and we use that to somehow merge the data of 2 data frames. So we'll look at that merge. So look at merge and concatenation is a simpler case. Merge is a more complicated case. Yeah, that's the basic idea of this lesson. So if you haven't already, so it says you will need to load the species and surveys files into Pandas. So if you haven't already grabbed it, I'll find a link to the species file from the very beginning. See, right, so at the very beginning of the setup, there was a species and species subset.csv. I'll put this in the Etherpad in case you don't have it already. Species.csv. So I'll put the link in the Etherpad. I'll put it in the chat as well. So you want to download this file, and if it isn't already in the directory with data where presumably the surveys file was, if it wasn't already there, then make sure it's there. There was a zip file I think linked here originally, which contains. See that's useful here. There's a zip file linked which contains everything. So if you already downloaded that, you're good. You will have that. If you've unzipped that, you'll have all the data necessary. And you'll also need this species subset.csv. sorry, what I pasted in just now is, yeah. Yeah, okay, that's fine, that works, I think. Put it in Etherpad as well. Okay. Right. So if you haven't already read in the service file, let's read that in, and then we'll read in the species file as well. So is there anything different that we're doing here? So you can see that in the example they've given a few additional options to read CSV, namely keep default NA as false and NA value equals when it's nothing. So as they themselves say here, I think we use some additional options that we didn't use previously. We have explicitly requested to change empty values in the CSV to nans. This is, however, also the default behavior of read CSV. So they've explicitly specified some options, but the options correspond to the default. So they don't actually change anything about what would result if we just use the default. I don't know exactly why they've done that, but so we can just call it like that, and that should give us something sensible, and we can check. And it does indeed. We can recognize this data from the CSV file when we just looked at it in the terminal. So the example here. So let's say let's take the example where we are combining two data frames. So feel free to follow along and try this in the terminal. I might, yeah, I can try this just so you can see as well. So the idea is being if you have a subset of a number of elements in your data frame. So for example, if you say take the 10 first rows in the survey's data frame. What does that look like? Rows 0 through 9, with some nans included, etc. Then let's also separately in a separate variable store the last 10 rows from our surveys data file. That's what that looks like. Then there's something here which talks about resetting the index, which I'm not going to do right away because I think it makes more sense to see what happens if you don't do that, and then to understand why you need to do that. So the idea is that we want to somehow combine these two data frames, right? We've got these two data frames now, one data frame containing the last 10 values and the other one containing the first 10 values. And let's just say we want to create a new data frame that has the first 10 rows of that new data frame are the first 10 rows of the entire data frame, the original one, and then the second set of 10 rows are the last rows. In other words, we just want to take a copy of the second of this last and underneath the first. So how can we do that? We can use the concat command, the pandas concat command, to concatenate two data frames. It takes the following arguments. So it takes a list as an input argument, a list of data frames that you want to concatenate. Most simply two. I assume it can take more than two, but we're just doing two. So which ones did that one? And that one. So let's see what happens if we specify nothing else. Let's see what happens. Okay, so it looks kind of right because since the data is all similarly structured, it knows exactly that the record IDs of the first data frame, well, of the second data frame should be concatenated and should appear underneath the record IDs of the first data frame. It notices that there's a correspondence exactly between the columns and i.e. series within the two data frames. So Pandas is happy to just do that. The additional input argument of axis equals 0. Let's see if that changes anything. Doesn't look any different. So what about if the axis was a different value? The axis was 1. So this does change something. And this will be what we will see later is actually, it's a bit hidden here. Okay, so that's actually corresponds to the trying to place the data frames side by side. So although it's not obvious from my terminal window here because it's too narrow, if I made it make it a bit wider, you'll see that what it's tried to do is it's tried to somehow add this. Yeah, okay, thanks, Evgeny. It's tried to add the side by side. But let's go back to what it says to do, which is the axis is 0, which, by the way, which appears to be the default anyway, which, by the way, corresponds to, I think you can also call it axis equals rows. Yes, that's right. One or the other, the number or the label might be easier for you to remember, but they are equivalent. So what has that done? It's stacked the data frames one on top of the other. So I'll do what they've done, call that my vertical stack. So there's one thing that doesn't quite look right or good or right about this if we're going to use this data frame and maybe use the index to address elements of it, which is that obviously this goes from 0 to 9 and then it skips ahead to 355 and 39 to 35548. So that's why there was this additional step here when initially specifying the last 10 lines, which was to reset the index. So let's see what that gives us. If we reset the index without any input argument, if we just call reset index, okay, that gives us now a data frame with the data from the last 10 lines with a first column, the index that actually is, as we might expect it to be, 0 through 9. However, with an index value here, which is reflecting the old index, which we don't necessarily care about. So we can drop that. And that's why the argument had this drop equals true. So what that is saying is that when you create this new data frame that has this reset index as the actual index 0 through 9, ignore the old index, just don't include that in the new one. So then you can see there's no column called index. It's just the index, the unlabeled index column, and then the record ID. So if we make survey sub last 10 equal to that, and then redo our concatenation to create our vertical stack, and look at what our vertical stack looks like now, that kind of looks right, but also kind of doesn't, because as they say here, have a look at the vertical stack, notice anything unusual, the row indices have been repeated. I go from 0 to 9, then 0 to 9. So it even wasn't quite enough. You can, okay, you can now re-index it as well by resetting index here. So actually, we could have just waited with resetting the index. It was kind of pointless. Purely for the sake of, if all we were going to do was create this vertical stack, we could have just waited with resetting the index until here. So we can reset the index now and again say drop equals true to not include the original index as a separate column. So now this looks all as we expected, 0 through 19. I, just as a point, so calling reset index on vertical stack hasn't actually changed vertical stack itself. It's just spat out as output the result of resetting the index on vertical stack. So if you check vertical stack, it still has this repeated 0 through 9, 0 through 9. So that's why we're constantly setting the left-hand side vertical stack equal to the result of the right-hand side doing something on it. So these operations, so if you have a function where, method where, say reset index did change vertical stack in situ, and that's what we call an in-place modification. So that immediately changes the underlying data, and then potentially prints it out to screen as well. But all that this does is prints that out as an output, and you still need to assign the result to the left-hand side to actually update vertical stack. So now we've set that explicitly. vertical stack itself has been changed and actually has that structure. Okay, so just about 11 o'clock almost, but we can also do horizontal stack. Yeah, we can look at that after the break. Feel free to have a look, and if you're doing anything other than just simply taking a break, you can have a look at this challenge already if you like. But yeah, take a quick break now, coffee tea break, and reconvene at 11:15. Okay. So I hope everybody had a good tea and coffee break. And so we'll just have a quick look before trying the challenge. We'll just have a quick look at this difference between horizontal stack and vertical stack. So these two different ways of concatenating. So here above we had this example where we're saying if we tried the vertical stack case. Now we're going to do the exact same thing apart, except for the axis along which we concatenate is going to be 1, i.e. columns. I can also call it columns rather than rows. And let's have a look at the result. Yeah, so I mean, we had a brief look before. So basically what's happened is, and it's a little bit hidden because with these dots, you can see that there's a number of columns that are hidden. It's hard to do that because, well, no matter even if your display is wide enough, it just decides to hide them, just like how it decides to hide the columns. It only shows a limited number of columns when you printed out the data frame. Basically what's happened is, there's still 10 rows, but now there are 18 columns rather than 9 columns. So as the name suggests, this horizontal stacking has basically taken the survey sub last 10 data frame and put it just next to the right of, so basically of the original of this survey sub data frame. So you've got now 2 sets of columns which are identical. So this is probably not what you want with this data that's structured identically. You typically probably want to have additional rows of the same with the same, so additional data points essentially with the same structure, same types of information appended or concatenated below the first set. But the typical example where you do something like this is where you have additional information, additional fields for the same data points, in this case, for the same observations. So if you have some additional information, but it's good to know you can do both depending on your need. So then, oh yeah, so you can try, by all means, I'd encourage you to try just checking that you can write this out to CSV and then looking at the file in the terminal or however you want to look at it, File Explorer. Yeah, great. Good. Sorry, I'm just saying Catherine's message saying that something has worked. Great. Yeah, so have a look at this challenge about combining data. So it basically talks about reading in these 2 input files. If you haven't got them, I'm not going to put the link because I assume people can find it. But if you have any issue finding these files, don't yet have them, just let me know in the chat, and I'll put the link in. And yeah, so have a look if you can combine the data from those 2 files into a single data frame, and then use that to create a plot of mean weight. A plot of average plot weight. See, I don't like the fact they use plot to determine they've got the plot ID in the CSV files, but that refers to the geographical site where the data was recorded, right? So the average plot weight says, so plot the average plot weight, so plot the average weight for each recording site, for each plot ID, by year, group by sex. So it's a couple of different kind of using the stuff you did yesterday about, and this morning we looked at by grouping things and selecting. Yeah, so give people a bit of time to work on that. So as you're working on the challenge, I might dip in and cover the first bit of it, and then maybe later on the second bit, just to help things along, might be useful. So I assume that the first step is fairly straightforward because it's basically reading in CSV data as we've been doing so far already. So for example, for the 2001, yes, we've can read in our 2001 and 2002 data. So we've got a data frame for each of them. We can see that they each have the identically named columns, and they have the same number identically named columns. They simply have different numbers of rows. So we want to combine those two into a single data frame. We use the concat command, just like before. Give it a list with two elements. First one is the first data frame. Second one is the second data frame. And then in principle, we could give it an argument saying the axis or dimension along which to concatenate. But I think the default should do the right thing. Correspond to a horizontal stack. Okay, that's right. So we probably want to reset our index on this result because we know that there'll be the first 1434 rows will have sequential indices, and then next 2078 rows from the second file that were concatenated will start at 0 again. So we just say service combined is service combined dot reset index. I'm going to say drop equals true because we don't care to keep the old index. So service combined. Now we see that the final index value of the final row is the number that you would expect if they all started at 0. If they start at 0 and just were incremented sequentially. Okay, so if that wasn't already obvious, you take a minute to try building the query to plot the average weight using that combined file now. Okay, so using our combined data frame, the question is asking us to plot stuff grouped by year and grouped by sex. So we know that we want to do a grouping. So we're going to say group by two things, group by year and group by sex. So I'm going to call that grouped by year and sex. And what do we care about? What value, what metric do we care about? We care about the mean weight. So we're going to take the weight from that grouped data frame, and we're going to ask it what is the mean. I've assigned that to a new variable, so what does that look like? That's what we expect. It contains what we care about for each year, for each sex. It contains the mean, weight, and then if we want to plot that, we could just try seeing if that will plot. It'll be a bar graph that we want. We'll see that it won't be quite what we want, but we'll see how to correct it. So this doesn't look quite like what we want because, if I expand this a bit, the undesirable thing is that it's created 4 categories here, which is it's labeled both year and sex as combined. So we would like to represent this a little bit more nicely. So this is due to our structure in the data frame, and if we unstack the mean weights before plotting, so if we unstack it, we get the F and M sexes as distinct columns. Of course, we can have if we unstack it again, we're going to go back to the original structure. So let's see what this how this plots. Okay, yeah. So this is what we want. So for each year, it shows the average weight for the 2 different sexes, as asked. Oh, it's export your results as a CSV and make sure it reads back into Pandas properly. Okay, I will leave that as an exercise, so you can output it like that. Write to CSV, and then if you want, you can read it back in. So let's see what they've done here. Index call equals 0. Interesting. So let's just have a quick peek at why they've included that. pd.read CSV question mark, and let's search for the search. If you're using rather than Jupyter Notebook, if you're using the terminal, you can use / and then enter a search term. So let's search index call, enter, and then N for next. So what is index column? Index column is columns to use as the row labels of the data frame. So it says use column 0, which is probably, because he used the same solution, I think pretty much as I did, column 0 of the weight. Let's see, so unstack. Here we go. So the weight here, the thing they're plotting includes the unstack, and that is the thing that is being written out to file, which therefore looks like this here, and therefore the first column has where it has the label sex, I think. So let's see if that's true. Mean weights CSV. If I write that out, it's the year actually. Yeah, it wasn't clear from this, I guess. Yeah. So it uses that as the. Let's read that back in. Right. Okay. So I think, not all people, but about half of you have finished that. So I hope that's, if you haven't indicated in the poll already, I hope that's clear. Any questions about that? Just say this plot.title layout. I don't know. That didn't seem necessary for me. I don't see a big difference in the plot that is produced here and the plot that I made. Maybe in your case, who knows? Maybe it did. So I noticed somebody mentioned that they didn't complete the challenge, maybe because there was an issue. If there's any issues, just see it might be able to help resolve. One case where mysteriously something that worked yesterday, Jupyter Notebook, now wasn't working today. The question is, the answer, solution is with so many things, tech, it's just, have you tried turning it off and on again? I just simply closing Jupyter Notebook entirely and restarting it. You shouldn't need to, but I mean, who knows? It was a bit of a cryptic error message. So I think the session, like an IPython session, it does store the the variables that you've initialized and read in. They should be retained from, I don't know, for example, if you shut down your computer overnight or something, it should be retained in the session in memory and then loaded up again when you restart the IPython session or Jupyter Notebook session if it's still active, if you haven't closed it. So the data in memory shouldn't have disappeared from memory. So things you've loaded should still be there. But yeah, okay. So let's. If there's no questions about that, let's continue. So we've done now the first part of this episode, which is about combining, concatenating and merging data frames. So now we're going to do the slightly less simple stuff, a bit more complicated. So now we're going to talk about joining data frames. So with concatenation, we're simply stacking them next to each other or one below the other. But now with joining, we're going to combine information somehow. So example here is that there's a subset, species subset file, which is useful to show an example. So if we read in, if you don't have this file, then link is in the setup for the course. So let's read that is the species subset. So it's simply 3 distinct species IDs. And we're going to use this as an example just to see how the join might work. At the same time, we're going to again get something we already had. We already used this subset of 10 first lines of the surveys data frame. And okay, so this talks about identifying join keys. So join key is basically a field that is shared between 2 data frames, which allows you to tell Pandas to merge the 2 data frames based on that shared key, because that's you somehow have to map the data from one data frame onto the other data frame. So the join key in this case is clearly the species ID, because in both the species data frame and the survey data frame, we've got this 2-letter species ID code, which is shared. So now we can somehow combine the data from these 2 data frames. So the question is, what does that mean? What it means is where we are, so we can do different things. We can, one option would be to expand the, so yeah, it's basically a case of expanding the data, so creating a new data frame that combines information from both, so that where, for example, the additional information about the genus name, species name, and the taxa name, that is going to be included in a new data frame, as well as the already existing information about the observations. So you're creating a new data frame that contains information from both. And there's different ways of doing this, a merge, 3 different ways. They're called a inner join, or a left, or inner merge, and a left join or left merge, and a right join or right merge. And basically the difference between those three different ways of merging the data amounts to what you decide to do with cases where there is data, there are, where there's data in one of the two data frames, but not in the other data frame. So the default join option is called an inner merge. So what we do there is that we only, so this is a visual representation of what the resulting merged data frame, what data that will contain compared to what data was in the original table and what data is in the second table or second data frame. So an inner join is the case where you only include data in the new joined or merged data frame where there is data present in both of the original two data frames. So the command for merging is pd.merge. And when we merge two data frames, so we give a, we specified, you might think we specified as a list, but no, we don't. There's arguments that we give as follows. We say the first data frame, that left data frame, is in this case this subset, the small subset of survey data called survey sub. The second data frame, the right data frame, is our species sub. Just do this, and it'll become a bit more obvious what we mean about what's included, what data is included in the merged one and not, once we look at the result. And then, in principle, we could actually proceed right now, because Pandas is clever enough to figure out that if you were to simply ask it to merge to merge survey sub with species sub, it's clever enough to notice that they have a column ID in common, namely something called species ID. Now, because it's called the same thing, and so it says, okay, that's fine. It's clever enough to just do that. You can, in principle, tell it what the shared join key is by saying join on what key, join on the key species ID. And in fact, if suppose that species ID wasn't called, although it's the same two-letter code convention in both data files, suppose for some reason it hadn't been called species ID, but it being called, I don't know, spec ID in one data file and species ID in another data file, then you could inform Pandas of that by saying, you know, my join key on the left, so in the first data frame, that join key is called species ID, and in the right, it is called potentially something else, spec ID or whatever. But we know it's species ID in both cases here, so we can explicitly specify that if we want to, even though it's the same. We can just say on, which stands in for left on and right on is the same species ID, or we can just leave it out entirely, and Pandas will be clever enough to work it out. Can you join on multiple keys? In a given operation, possibly. Let's see. Label or list. Okay. Column or index level names to join all these must be found in data frames. Possibly, yeah. Right now, we're not going to try that. We'll just try merging on the singles. A simple example of joining just on the obvious key. Right. So what's happened? You can see that there is. You can see that there. This is the looks a bit like the original data with a few additional columns corresponding to the data that was in the species file, namely genus, species, and taxa, where the species ID column has remained where it was in the original left data frame. And clearly that's what's being used to pick out the correct data from the right data frame. So where it's an L, it's picked out neotoma, where it's DM, it's picked out dipodomes, etc., etc., etc. Now, one thing to notice is that so that's the number of columns, but look at the number of rows and the row indices. So it's 0 through 7 as opposed to 0 through 9. So what's happened there? Well, let's have a look. So there are clearly, yeah, as it says here, merge inner dot shape. I haven't assigned this to a variable. Let's call it merged inner, like I've done here. 8 to 12, exactly as I point out here. So what's happened is that there are, in that merge, there were some species IDs for which, there were some species IDs in the original survey data for which there was no corresponding two-letter code that could be found in the species data frame. Because our species data frame, on purpose, this situation was created because rather than having the full complete set of species two-letter codes, this subset only has 3 codes. So it's no surprise that perhaps some can't be found when you do the merge. Because we have done an inner merge, where what we're asking is to get the case where we have a new data frame that only contains entries where we have data for that join key present in both data frames. It has excluded data from the original, from the left data frame, where the species ID, the join key, is a value that was not present in the key. Now, we can see in the original data that in the survey data that NL is fine. NL is present in the species ID subset. DM is fine. That's present here as well. PF is not fine. PF is not to be found as a join key in the species sub data frame. So that means that when we do the inner merge, this row from the survey sub will be excluded, and this row from the survey sub will be excluded because they both have PF as a species ID. P is fine, DM is fine, so that's it. Those 2 rows are missing, and indeed that reduces the number of rows from 10 to 8. So that explains what you get if you do an inner merge. Apologies. Sorry, if you give me 1 second, I just need to tell a colleague that I'm not available for something. Okay, yeah. So we can also do, let's see if there's anything here that I didn't already mention. I think I've pretty much summarized that. If we want to do other joins, we can do a left join. So with a left join, what we're saying is that we don't mind necessarily if there's no information present in the right data frame corresponding to a join key value in the left data frame. We still want to keep the data that does exist in the left data frame. And it's just going to be, tough that we don't have corresponding data for these additional columns that are coming from the right data frame, like genus, species, and taxa, but we still want to keep that those values. We don't want to lose this. You could genuinely think of the case here, because you have these animal observations, these field observations from the survey, and you don't want to lose that just because you would happen not to have the genus and taxa information. In fact, you might want to plot that and be aware of that, because if it's unknown and it's not in your list of recognized genus and taxa, then you want to know and find out what's going on. So if we do this merge left, which is same, the only difference being that now we have this additional input argument that we didn't have in the first case, saying how, i.e. how to merge. We say now left. The default would be how is inner, I suspect. Then yeah, again, this is explicitly specifying the join key. We don't need to, because Pandas is clever enough to figure it out, because it's still called the same thing in both data frames, namely species ID. The two data frames are the same. The only difference now is we say how is left. So what does merge left look like? Well, merge left.shape is, it's not a function, it's an attribute. Is the same number of rows as survey.sub, and you can see now that these two rows where the species ID is PF are still there now, and their genus, species, and taxa is now simply given as nan, right? So yeah, and I guess you can extrapolate from this that if we were to finally do a right merge, leaving everything the same apart from right, what we get then is that we only keep, yeah, in fact, this doesn't show anything, yeah, because there are no species ID. This looks identical to the inner merge because there are no species IDs in the species sub that don't exist in the left data frame in the survey sub, because there are no known species ideas that don't appear in that survey sub. Okay. So yeah, so that's the outline of merging. I think that probably yeah, I've talked about. Okay, there are other kinds of merges as well, which, yeah, if you're interested in, you can look into that. I don't think you need to know that for the exercises. So this is an opportunity to try playing around with this, joining the contents of the, now working with, so for this challenge, working not with a subset of surveys and species data frames, so working with the full data frames read in from these files. So yeah, so I'd say go ahead and try this. I would skip the, unless, I don't think anybody was actually into doing ecology, but I suggest we skip this diversity index challenge. This gets very ecological. I mean, I think what's more important is that most of the conceptual stuff and also practical experience, I think, is covered in just going through this challenge yourself and plotting something that results. This diversity index thing is, biodiversity index thing is, it's just more figuring out something that I don't think necessarily teaches you that much new that you wouldn't possibly forget and just need to refigure out again once you get to your own problem in the future. So I suggest we skip this diversity index problem, but it's worth getting some practice in doing this distribution challenge. So yeah, so I suggest you get on with that now, and then we can have a look at that after the lunch break. I quickly summarize after the lunch break, and after lunch we will proceed with data workflow and automation. We'll start making some plots as well. Data workflows and automation will be fairly quick. We can skip some of the exercises if need be, because it's basically defining some functions and input arguments. So if anything is unclear as I talk through that, then I would suggest you ask questions. But I think it's nice to get to some of the plotting. So we'll make sure we get to that before the end of the course today. Right. So I'll be here until be online until 12, and then from 12 just go and have lunch and meet again at 1 o'clock. If you have any questions, just pop it in the chat.
Hi, can I ask by audio? I think it's clearer for me. So I was working on this joining data frames last week, and well, I had problems because my two databases are complex because they have a lot of individuals, and also I use a software that filters automatically some genomes, right? So on my metadata database, I had some individuals that were filtered, so I didn't have the same sample length. So I needed a loop to iterate through each row, so through each individual, see if that individual was in one database or data frame, and then copy all the information in the other data frame. Yeah.
Yeah, that's one way to do it. Or at least it worked. Did it work? Did it work?
I needed help, and I use Python, not Pandas. But I'm wondering if Pandas would be easier to do this. So well, based on this, so I have the same name column based on sample ID. So the same species ID. I had sample ID. That was the key in both data frames. So I wanted to copy the information based on that column. Yeah.
So you were trying to create a merged just so I get it right. You were trying to create a merged one based on those two data frames, or you're trying to copy what from where to where?
Yeah. So I wanted to do a PCA. Okay. So I had my eigenvec file with all my eigenvec columns, right?
Okay. I don't know anything about PCA, but
yeah, right. Sorry.
No, that's fine.
So
I'm trying to follow along.
On that basic file, I wanted to add the information for the metadata of each individual, because I only had the sample ID of each individual. But the problem is that in my eigenvec file, I got individuals that were removed, that were filtered
by the software.
So they didn't match. So because if they match, I could just, it would be like very easy. I could have just copied them. But so I did a loop. I created a loop to iterate into the first database, the one without filtered individuals. And then based on if they had or not that sample ID. If that sample ID was present on the first database, then copy all this information for this individual in the eigenvec file in the second data frame.
Yeah. And so
that works. It's like joining. It's like this. It worked manually after like a week of trying different ways. Yeah, but I think with Pandas, I didn't try, but I think it would have been faster. So I just
I think I can imagine. So I mean, I can't on the spot kind of imagine exactly how we do it, but I imagine that it should be easier because rather than going in and manually checking all kinds of stuff, you should in principle be able to use some kind of combination of the selection criteria, the way of checking for presence or not, or checking what these joins will, I guess, they're kind of intersections, right? So checking for it should allow you to have higher level operations to check for the presence or absence, and to have selection criteria and to modify things based on the selection criterion. So you could have something that yeah, I imagine it should be possible to do it less manually, more again a bit more at a higher level, and without also being as error prone potentially as setting things manually. And then hopefully more reproducibly as well, because if you can simplify that as yeah,